You think diamonds shine because they're pretty rocks. Wrong. Inside every diamond sits a quantum machine that traps light, bends physics, and glows brighter than systems burning at 10,000 degrees. Scientists call them Nitrogen-Vacancy centers. The rest of us just see red, walk into any physics lab with a green laser and a Type 1b diamond, hit it with 532 nanometers. Watch what comes back. 637 nanometers. Bright red light that doesn't stop. Not for hours, not for days. The photoluminescence quantum yield sits at 70 to 80%. That means for every 10 photons you pump in, 7 come back out as visible light. Stars? The sun converts 0.000045% of its mass into visible light. A diamond color center running at room temperature outshines stellar fusion by orders of magnitude per atom. Here's what nobody tells you about that red glow. It's not coming from the carbon. A nitrogen atom sits where a carbon atom should be. Right next to it, one carbon atom is just gone. Missing. That's the vacancy. Nitrogen plus vacancy equals NV center. The negatively charged version, NV negative, holds 6 electrons in a lattice position designed for 4. 2 electrons pair up in a spin triplet ground state. Quantum spin equals 1. That configuration stays coherent at room temperature for milliseconds. Up to 1.8 milliseconds in ultra-pure carbon, 12 enriched diamond measured at Cambridge in 2012. Room temperature quantum coherence lasting longer than 1,000th of a second. No other solid-state system comes close. If you value documented quantum physics and material science history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual, using sources from Nature Communications, published November 10th, 2025, showing 1. GeV gold and uranium ion tracks creating NV center chains, and from Physical Review, B, July 27th, 2018, detailing silicon vacancy vibrational modes with Wang-Riesz factors, confirming deep electron phonon coupling data from density functional calculations on supercells containing thousands of atoms. Now back to the information. The quantum mechanics get stranger. When you hit an NV center with a photon at exactly 532 nanometers, the electron jumps from the 3A2 ground state to the 3E excited state. That's a triplet-to-triplet transition. Spin stays constant. The excited state lasts 13 nanoseconds in bulk diamond, 25 nanoseconds in nanodiamonds, because the refractive index changes how fast light escapes. During those nanoseconds, the electron can do 2 things. Drop straight back down and emit a photon at 637 nanometers. That's the 0 phonon line. Or it couples to lattice vibrations, phonons, and emits at longer wavelengths between 630 and 800 nanometers. That's the vibronic sideband. The ratio matters. In NV centers, the Wang-Riesz factor sits around 3 to 4. That's electron-phonon coupling strength. It means roughly 30% of emission happens at the 0 phonon line. 70% spreads into the phonon sideband. Compare that to organic dyes, where the 0 phonon line vanishes at room temperature. Diamond defects keep a sharp spectral feature even when the lattice is vibrating at 300 Kelvin. The 0 phonon line has a full-width half maximum of about 5 nanometers at room temperature. Cool it to liquid nitrogen temperatures, 77 Kelvin, and it sharpens to 1.2 gigahertz, measured by nanoletters, in 2012 from isotopically purified samples. Why does this matter for brightness? Because the 0 phonon line is where the action happens for quantum sensing. The photons come out at a precise wavelength. The emission rate depends on the magnetic field, electric field, temperature, strain. All those variables shift the energy levels by small amounts. 74 kilohertz per Kelvin for temperature. The crystal field, splitting at room temperature, sits at 2.870 gigahertz. Apply a magnetic field along the NV axis, and the spin states split further. That's the Zeeman effect. Each Tesla of magnetic field adds 28 megahertz to the splitting. Read that splitting optically, and you've built a magnetometer. Sensitivity down to 1 nanotesla per root, hertz demonstrated by NEST in 2025. The brightness comes from photon flux. One NV center excited at saturation emits about 300,000 photons per second. That's the count rate you get with a good confocal microscope and avalanche photodiodes. 3 times 10 to the 5 per second from a single quantum emitter. The quantum yield of 70 to 80% means most absorbed photons convert to emitted photons. Very little energy gets lost to heat. The radiative lifetime of 13 nanoseconds sets the upper limit. Faster than that, and you're fighting the Heisenberg uncertainty principle. Slower and non-radiative decay channels start winning. Now compare to stars. The sun's photosphere sits at 5770 Kelvin. It emits across the blackbody spectrum, peaking around 500 nanometers. Total luminosity 3.8 times 10 to the 26 watts. Sounds impressive until you calculate per atom. The sun contains 1.2 times 10 to the 57 hydrogen atoms. Divide luminosity by atom count. You get 3 times 10 to the negative 31 watts per atom. An NV center at saturation with a 13 nanosecond radiative lifetime emits about 4 times 10 to the negative 19 joules per photon at 637 nanometers. At 300,000 photons per second, that's 1.2 times 10 to the negative 13 watts per atom. The diamond wins by 18 orders of magnitude. That's not a fair comparison because stars don't work like lasers. But here's what is fair. Nanodiamonds containing NV centers get internalized by living cells. 50 nanometer particles pass through cell membranes. Once inside, you can track them optically for days. The photostability is perfect, no photobleaching. Quantum dots blink, organic dyes fade. NV centers don't. They sit in a diamond lattice with a 5.5 EV bandgap. Nothing in a biological environment has enough energy to damage them. You can image single nanodiamonds under continuous illumination for hours and the signal stays constant. Studies from 2009 compared NV nanodiamonds to cadmium selenide quantum dots. At saturation, the nanodiamonds emitted 3 times less intensity than quantum dots, but the quantum dots blinked on timescales of milliseconds. The nanodiamonds never blinked. For long exposure, imaging the diamond is brighter because it's always on. The quantum coherence is the real trick. The electron spin in the NV negative ground state splits into 3 levels. M sub s equals 0 plus 1 minus 1. 0 sits lower by 2.87 gigahertz at 0 magnetic field. That splitting comes from spin-spin interaction. No magnetic field needed. Hit the center with a 532 nanometer laser, and you optically pump it into the M sub s equals 0 state. The triplet excited state has a decay pathway through a singlet manifold. That singlet pathway is spin selective. M sub s equals plus or minus 1. States are more likely to take the singlet route. They end up back in the ground state without emitting a photon. M sub s equals 0 almost always emits. So after a few cycles of excitation, most NV centers sit in M sub s equals 0. That's optical initialization. Efficiency above 95%. Once initialized, apply microwave radiation at 2.87 gigahertz. That's resonant with the 0 to plus 1 transition. The spin flips. Now the NV center is in M sub s equals plus 1. Optically, rid out the state by measuring fluorescence. M sub s equals 0 is bright. M sub s equals plus or minus 1 is dim. You've just measured the spin state using light. That's optically detected magnetic resonance, invented for NV centers in the 1990s. The coherence time sets how long the spin state survives before random magnetic noise destroys the information. In natural diamond with 1% nitrogen, coherence times sit around a few microseconds. That's interaction with nitrogen nuclear spins in the lattice isotopically purify the diamond to carbon-12. Nitrogen concentration below 1 part per million. Coherence times jump to milliseconds. The record is 2.4 milliseconds measured at room temperature by researchers in Japan using phosphorus-doped N-type diamond published in Nature Communications, August 2019. Millisecond coherence at 300 Kelvin. That's quantum information surviving thermal noise. Dynamical decoupling extends it further. Flip the spin repeatedly with microwave pulses. The flips average away slow magnetic fluctuations. Each flip acts like a spin echo. Apply thousands of pulses, and you can push the coherence time to approach the T1 limit. That's the longitudinal relaxation time. For NV centers, T1 sits around 6 to 7 milliseconds at room temperature, so the coherence is already at 85% of the fundamental limit. Nothing else in solid-state quantum systems comes close to that efficiency at room temperature. The spin coherence enables quantum sensing that stars cannot match. Apply an oscillating magnetic field at the spin resonance frequency. The spin flips back and forth, the fluorescence oscillates. Lock in to that oscillation, and you're measuring AC magnetic fields with nanotesla sensitivity, bandwidth from DC up to gigahertz. Spatial resolution set by the laser spot size, diffraction limited to about 250 nanometers with visible light. Put the NV center within nanometers of the sample surface, and you're measuring magnetic fields from single electron spins. Demonstrated for nuclear magnetic resonance of molecules on the diamond surface. Single molecule NMR using quantum diamond sensors. Temperature sensing works the same way. The crystal field splitting shifts 74 kilohertz per Kelvin. Measure the splitting and you know the temperature. Thermal sensitivity better than 10 millikelvin per root. Hertz achieved using dynamical decoupling by researchers at Harvard, published in PNAS in 2013. 10 millikelvin inside a living cell with nanometer spatial resolution. No other thermometry technique gets close. The physics behind the zero phonon line reveals why diamonds work. Electronic transitions happen in femtoseconds. Nuclear motion happens in picoseconds. The Frank-Condon principle says, during the electronic transition, nuclei don't move. You go straight up on an energy diagram. That's a vertical transition. If the excited state minimum sits directly above the ground state minimum, you get a strong zero phonon line. If they're offset, you get strong phonon sidebands. NV centers have moderate offset, Wang-Riesz factor of 3 to 4. That gives you both. A sharp zero phonon line for precision measurements, a broad phonon sideband for high total count rate. The phonon sideband structure maps the vibrational modes of the lattice. Diamond has one Raman active mode at 1,332 wave numbers. That's the symmetric stretch of the carbon-carbon bonds. In the NV center, phonon sideband, you see replicas of the zero phonon line shifted by that phonon energy. First replica at plus 165 MeV. Second replica at plus 330 MeV. The intensities follow Poisson statistics determined by the Wang-Riesz factor. At room temperature, thermal population of phonons broadens everything. Cool to liquid helium temperatures, 4 Kelvin, and the phonon structure becomes visible. Individual vibronic transitions separated by the phonon energy. Why does the zero phonon line survive at room temperature when organic molecules lose it? Diamond is stiff. The carbon-carbon bond length is 1.54 angstroms. Bond energy 3.6 eV. That's one of the strongest bonds in chemistry. The lattice barely moves even at 300 Kelvin. Thermal expansion coefficient of diamond is 1 times 10 to the negative 6 per Kelvin, compared to silicon at 2.6 times 10 to the negative 6, or germanium at 6 times 10 to the negative 6. Diamond lattice is locked in place. That rigidity preserves the electronic transition energy against thermal noise. The zero phonon line shifts with temperature, but it doesn't wash out. The quantum yield of 70 to 80% comes from the rate competition. Radiative decay, rate 1 over 13 nanoseconds equals 77 megahertz. Non-radiative decay rate includes intersystem crossing to the singlet manifold. That singlet state lives about 250 nanoseconds. The singlet can decay back to the triplet ground state or emit a phonon and drop to a lower singlet level before crossing back. The whole process adds a non-radiative pathway. But it's slow compared to the direct radiative decay, so most photons come out 70 to 80%. If you put the NV center in an optical cavity, you change the game. The cavity modifies the local density of photonic states. That changes the radiative decay rate. A high Q cavity can increase the radiative rate by the Purcell factor. For a cavity with quality factor 4,000 and mode volume of a few cubic wavelengths, the Purcell factor reaches around 10. That multiplies the radiative rate by 10. Decay time drops from 13 nanoseconds to 1.3 nanoseconds. Photon emission rate goes up. The zero phonon line gets selectively enhanced if you tune the cavity mode to 637 nanometers. The phonon sideband doesn't couple to the cavity as strongly because it's off resonance. Result, sharper emission spectrum, faster photon rate, better collection efficiency. Researchers fabricated diamond microdisc resonators and got spontaneous emission rate enhancements of factor 10 for single NV centers published in Nature Photonics in 2010. Ion implantation creates NV centers on demand. Take ultra-pure diamond grown by chemical vapor deposition. Implant nitrogen ions at specific energies. 2 MeV helium ions for deep implants. 15 keV nitrogen ions for shallow implants. The ions knock carbon atoms out of the lattice, creating vacancies. Anneal at 800 degrees Celsius. The vacancies diffuse and trap at nitrogen sites. NV centers form with conversion efficiency around 10%. That means 10% of nitrogen atoms end up paired with vacancies. The rest stay as substitutional nitrogen or aggregate into other defects. Recent work uses 1 GeV gold and uranium ions. Those heavy ions create damage tracks along their trajectories. Vacancies and vacancy clusters form via electronic stopping. Not nuclear collisions. The ions transfer energy to electrons, which knock out atoms. The damage track is one-dimensional. Annulate and vacancies migrate to nitrogen atoms, creating chains of NV centers. Published November 10th, 2025, in Nature Communications Materials. The chains appear as bright luminescent strings in confocal microscopy. Each string is a single ion track containing dozens of NV centers, spaced a few nanometers apart. Spin coherence times in these chains remain competitive with isolated centers, T2 around 100 microseconds. Shallow NV centers matter for sensing. You want the defect close to the diamond surface, within 10 nanometers. That puts the spin close to external magnetic or electric fields, but surfaces introduce noise, dangling bonds, adsorbits, charge traps. All of that shortens coherence time. Surface termination matters. Hydrogen termination gives longer T2 than oxygen termination. The best surface treatments achieve T2 star, that's inhomogeneous dephasing time, around 1 to 2 microseconds for NV centers 5 nanometers deep, compared to bulk NV centers at 50 microseconds. The surface kills coherence, but the trade-off is worth it. 5 nanometers from the surface and you can detect single nuclear spins outside the diamond. Nanodiamonds are cheap. about $1 per gram for 50 nanometer particles. Made by detonation synthesis, or milling of larger diamonds. Contains 10 to the 7 NV centers per particle if you implant and anneal properly, bright enough to see single particles in wide-field microscopy. Fluorescence, nanodiamonds, FNDs, with NV centers get used for cell tracking, drug delivery monitoring, thermal imaging, and microfluidic devices, all at room temperature with no photobleaching. Stars fuse hydrogen into helium. 4 hydrogen nuclei combine to make 1 helium nucleus plus 2 positrons, plus 2 neutrinos plus energy. Total energy released 26.7 MeV per fusion. The sun fuses 620 million tons of hydrogen per second. Sounds like a lot. But spread over 10 to the 57 atoms, each atom contributes negligibly. The sun will burn for another 5 billion years precisely because fusion is so inefficient per atom. The core temperature is 15 million Kelvin. Pressure, 250 billion atmospheres. Even in those conditions, fusion is rare. The sun glows from volume, not from atomic efficiency. An NV center glows from quantum efficiency. Every photon absorbed has 75% chance of coming back out as visible light. The process runs at room temperature, atmospheric pressure, no fusion required. The brightness per atom exceeds stellar fusion by factors measured in dozens of zeros. The NV center doesn't burn fuel, it just cycles. Absorb photon, emit photon, repeat. The diamond lattice doesn't degrade, the nitrogen doesn't migrate, the vacancy doesn't move. Run it for years and nothing changes. Test it, and you get the same fluorescence curve. That stability stars cannot match, because stars consume themselves. The Phonons sideband physics explains diamond color. Nitrogen aggregates in natural diamonds absorb blue light. The N3 defect has a 0 phonon line at 415 nanometers. That's violet. The absorption tail extends through blue into green. Result, yellow diamond. The NV center has its 0 phonon line in the red. Absorption in the green, emission in the red. A diamond with high NV concentration looks pink under white light. Not from the 0 phonon line alone. The whole phonon sideband contributes. Red through near infrared. Silicon vacancy centers are even sharper. 0 phonon line at 738 nanometers. Full width, half maximum less than 1 nanometer at room temperature. The silicon atom sits at the vacancy with symmetry. The Huang-Reis factor drops to around 0.1. That means 90% of emission happens at the 0 phonon line, 10% in the sideband. The line is so sharp you can see isotopic shifts. Silicon 28 versus silicon 29. The 0 phonon line shifts by a few nanometers. You can resolve it with a good spectrometer. SiV centers couple to acoustic phonons more than optical phonons. The excited state lifetime is longer, around 2 nanoseconds. So the count rate is lower than NV, but the spectral purity is higher. Germanium vacancy centers shift even further into the infrared. 0 phonon line at 602 nanometers measured in 2021. Tin vacancy centers are being explored. Each group IV element creates a different defect with different optical properties. The periodic table becomes a toolbox for designing color centers. Quantum networks need identical photons. 2 photons from 2 separate emitters must be indistinguishable. Same wavelength, same polarization, same temporal mode. NV centers in diamond have a problem. The 0 phonon line at 637 nanometers is still too broad. Inhomogeneous broadening from local strain. Each NV center sees a slightly different environment. Its 0 phonon line shifts by a few gigahertz. When you try to interfere photons from 2 NV centers, the visibility is low, around 60% at best published in Physical Review Letters in 2012. Silicon vacancy centers do better. The sharp 0 phonon line and weak electron-phonon coupling mean less inhomogeneous broadening. Researchers got 2 photon interference visibility above 90% from SiV centers and cavities. That's quantum indistinguishability. The photons behave as if they came from the same source. Build a network of SiV centers and diamond cavities, and you have the start of a quantum internet. Single photons generated on demand, transmitted through optical fibers, and interfered at a beam splitter to create entanglement between distant nodes, all at room temperature or cryo temperatures depending on coherence requirements. Entanglement between NV centers was demonstrated in 2015. 2 NV centers separated by 1.3 meters in the same lab. Optically entangle their spins using photon interference. The entanglement survives long enough to perform a Bell inequality test. Result? Violation of the Bell inequality with high statistical significance. Proof that quantum mechanics correctly describes spatially separated systems. NV centers in diamond proved it. The long spin coherence time makes NV centers useful for quantum repeaters. Quantum communication over long distances requires repeaters to extend the range. Photons get absorbed or scattered in optical fibers. After a few hundred kilometers, the signal is lost. A quantum repeater stores the quantum state in a long-lived qubit, waits for confirmation from the next node, then reteleports the state forward. The NV center spin can store a quantum state for milliseconds. long enough to synchronize over intercontinental fiber links. The vision is a global quantum network with diamond nodes every 100 kilometers, storing and forwarding quantum information. Quantum computing with NV centers runs into trouble. The coherence time is long, but gate operations are slow. Microwave pulses take microseconds to flip spins. That's thousands of gate times within a millisecond coherence. Not enough for useful computation. Superconducting qubits execute gates in nanoseconds with coherence, times approaching milliseconds now. They beat NV centers on gates per coherence time by 2 orders of magnitude. So NV centers are better for sensing and communication than for computation. But hybrid systems could work. Use superconducting qubits for computation. Use NV centers for quantum memory and communication. Transfer the quantum state from a superconducting circuit to an NV center via a microwave photon. Store it in the NV spin. Read it out optically when needed. That combines the best of both. Fast gates from superconductors, a long memory from diamond. The ultimate brightness comparison isn't per atom, it's per volume. Pack NV centers into a thin diamond film at 10 parts per million. That's 10 to the 18 NV centers per cubic centimeter. Excite them with a focused laser beam of 1 micron diameter. The excitation volume is 10 to the negative 12 cubic centimeters. Contains 10 to the 6 NV centers. At 300,000 photons per second per center, the volume emits 3 times 10 to the 11 photons per second. That's 300 gigaphotons per second from a femtolighter. Collect 10% with high numerical aperture optics. You get 30 billion photons per second onto your detector, enough to saturate an avalanche photodiode. The brightness is limited by detector capability, not by diamond emission. Stars have lower brightness per volume if you integrate over the whole photosphere. The solar luminosity per cubic meter at the photosphere is about 2 times 10 to the 6 watts per cubic meter. Convert to photons at 500 nanometers, about 5 times 10 to the 24 photons per second per cubic meter. Sounds huge. But the laser excitation volume in diamond emits 3 times 10 to the 23 photons per second per cubic meter, with only 10% collection efficiency, a factor of 60 brighter per volume than the sun's surface. And this is room temperature diamond, not a fusion reactor. The reason diamonds win on brightness is quantum efficiency. Stars waste energy. 99% of fusion energy goes into neutrinos that escape without interaction. The sun loses 2% of its fusion energy to neutrinos. The rest becomes heat that takes 10,000 years to diffuse from core to surface. By the time it radiates, it's spread over a blackbody spectrum. Diamonds don't waste energy. The photon comes in, the electron jumps, the electron falls, the photon comes out. 75% efficiency. Quantum processes are clean. The infrared phonon sideband contributes to heating. That 70% of emitted light between 650 and 800 nanometers carries less energy per photon than the excitation at 532 nanometers. The difference becomes heat, about 0.4 eV per photon absorbed. At high excitation powers, the diamond warms up. Thermal conductivity of diamond is 2,000 watts per meter Kelvin, 20 times better than copper. The heat spreads fast. Even so, in a tightly focused laser beam, you can raise the local temperature by tens of degrees. That shifts the NV emission spectrum. The zero phonon line red shifts at 74 kilohertz per Kelvin. Use it to measure the local temperature, self-calibrating thermometry. Coherent quantum control of NV centers has been pushed to 1000 Kelvin, published March 2021 in Nature Communications. The trick is pulsed laser heating. Heat the nanodiamond with a nanosecond laser pulse. The temperature spikes to 900 Kelvin. Control the spin with microwave pulses during the hot phase. Then let it cool back to room temperature in microseconds by thermal diffusion. Read out the spin state at room temperature. The spin coherence survives the thermal cycle. T2 drops to hundreds of nanoseconds at high temperature, but it's still measurable. The demonstration showed optically detected magnetic resonance up to 800 Kelvin, and spin echoes near 1000 Kelvin. That opens high temperature quantum sensing. Magnetic phase transitions in nanoparticles, thermoplasmonics, heat-assisted magnetic recording, all above 600 Kelvin where other quantum sensors fail. The quantum yield staying at 70%, even at 800 Kelvin, is remarkable. The non-radiative decay rate must be temperature independent. Intersystem crossing doesn't speed up much with temperature, and the singlet state is higher in energy. Thermal population doesn't increase it, so the NV center keeps glowing hot. Literally. The photon emission rate stays high until you reach the point where the singlet becomes thermally accessible. That happens above 700 Kelvin. Then fluorescence quenches. The spin can still be controlled, but optical readout fails. Researchers solve that by cooling for readout. Diamonds outlast everything. Natural diamonds are billions of years old. Radioactive dating of diamond inclusions puts some at 3.3 billion years. Older than multicellular life, older than oxygen atmosphere, formed in the mantle, brought up by volcanic eruption, sitting in kimberlite pipes ever since. The carbon lattice doesn't degrade, the NV centers don't migrate at room temperature. Annual above 1000 Celsius and vacancies start moving. Below that, they're frozen in place. So a diamond with engineered NV centers will keep glowing for geological timescales. No other material matches that permanence. Synthetic diamonds grown by chemical vapor deposition control everything: isotopic purity, nitrogen concentration, crystal orientation, surface termination. Researchers grow 100-micron thick diamond films on silicon substrates, dice them into chips, pattern them with electron beam lithography, etch photonic structures, waveguides, cavities, nanopillars, all designed to extract photons efficiently. The best designs get photon collection efficiency above 10%, still limited by diamond's refractive index of 2.4. Total internal reflection traps most photons. Solid immersion lenses help. Etch a hemisphere on the diamond surface centered on the NV center. The lens couples light out at higher angles. Collection efficiency jumps to 30%. The future is quantum networks built on diamonds. NV centers as nodes, photons and optical fibers as links. Each node stores quantum information in nuclear spins, coupled to the NV electron spin. Carbon-13 nuclei in the diamond lattice act as quantum memory. The NV electron spin addresses them, coupling strength around 1 MHz. That's resolvable with dynamical decoupling. Individual carbon-13 spins can store quantum states for seconds, longer than the NV electron spin by 3 orders of magnitude. Use the nuclear spins as a quantum register. 5 carbon-13 spins give you 32-qubit basis states, enough for small quantum algorithms. Demonstrations already ran quantum error correction codes on NV nuclear spin registers, the 3-qubit bit flip code, the 5-qubit code, all at room temperature. Limited by gate fidelity, not by coherence time, microwave control of nuclear spins is slow and imperfect, but it works. The vision scales to arrays of NV centers, each with a few nuclear spin qubits, connected by optical photons. Distributed quantum computing with diamond nodes, or you go cryogenic, cool NV centers to 4 Kelvin. The 0 phonon line sharpens to its natural line width. 13 nanosecond radiative lifetime gives a Fourier limited line width of 12 MHz. That's how narrow it can get. Inhomogeneous broadening from strain adds a few hundred megahertz, but it's still much sharper than room temperature. The phonon sideband disappears at low temperature. All emission goes into the 0 phonon line. That increases the fraction of useful photons, and the gate fidelity improves. Microwave Rabi frequencies get higher because there's less thermal noise. Silicon vacancy centers are even better cold. At 4 Kelvin, the SIV 0 phonon line sharpens to tens of megahertz. Add it to an optical cavity and you get cooperativity, the ratio of coherent to incoherent scattering greater than 1. That's the strong coupling regime. The emitter and cavity act as one quantum system. Photon emission becomes reversible. The photon can be reabsorbed before it escapes. You can engineer the interaction to create deterministic photon sources. Press a button, get a photon, efficiency above 90%, or create photon-photon gates. 2 photons interact via the SIV center. Conditional phase shift, that's universal quantum computing with photons. All of this comes from a missing carbon atom next to a nitrogen. The defect is atomic scale. The quantum effects are macroscopic. The glow is visible to the naked eye in high concentration samples. Shine ultraviolet light on a nitrogen-rich diamond, and it fluoresces red. That's millions of NV centers emitting simultaneously, each one running its quantum cycle. Absorb, emit, repeat. 75% efficiency, millisecond coherence, no photobleaching, no blinking, room temperature operation. The Debye-Waller factor explains how the 0 phonon line intensity changes with temperature. It's the probability that a photon emission happens without creating or destroying phonons. Temperature increases lattice vibrations. More thermal phonons mean more chances for the electronic transition to couple with them. The 0 phonon line intensity drops exponentially with temperature. The exponential depends on the Huang-Reis factor and the temperature. For NV centers with S equals 3, the room temperature 0 phonon line intensity is about 30% of the total. Cool to 77 Kelvin and it jumps to 50%. Cool to 4 Kelvin and it hits 70%. The rest goes into phonon replicas. That's Mossbauer effect physics applied to optical transitions. Rudolf Mossbauer discovered in 1958 that gamma rays from iron-57 nuclei could be emitted without recoil if the nucleus was embedded in a crystal. The crystal as a whole absorbed the recoil momentum, made the gamma ray energy incredibly sharp. Same principle works for NV centers. The diamond lattice is so stiff that the electronic transition can happen without exciting vibrations. The nitrogen and vacancy don't recoil. The lattice absorbs any momentum. Result, sharp 0 phonon line even at room temperature. The dipole moment of the NV transition is large, about 18 dBi for the transition from 3A2 to 3E, measured by density functional calculations. That's comparable to organic dyes. Large dipole moment means strong coupling to light, high absorption cross-section, high emission rate. The radiative decay rate scales as the square of the dipole moment times the cube of the frequency. That's why visible transitions are so much brighter than infrared. The NV center at 637 nanometers has a radiative rate 77 megahertz. Move it to near infrared at 1000 nanometers and the rate drops to 10 megahertz. Brightness goes down. Phonon replicas in the emission spectrum map the local vibrational modes. The NV center perturbs the diamond lattice, creates localized vibrations. The quasi-local mode sits at 64 MeV. That's the breathing mode of the nitrogen, and its 3 nearest carbon neighbors. Shows up in the phonon sideband as a shoulder on the main peak. Resonance Raman spectroscopy resolves individual vibronic transitions. Pump with a tunable laser, scanning across the zero phonon line. Watch the scattered light spectrum. When you're resonant, vibronic peaks light up. Their positions and intensities reveal the electron-phonon coupling for each mode. Isotope effects prove the assignments. Replace carbon-12 with carbon-13. The lattice gets heavier. Phonon frequencies drop by about 3%. That's the square root of the mass ratio. The quasi-local mode shifts from 64 MeV to 62 MeV. Vibronic peaks in the spectrum shift accordingly. Replace nitrogen-14 with nitrogen-15. The nitrogen vibration slows down. Different shifts. By comparing isotopes, you figure out which atoms are moving in each mode. Silicon vacancy centers have different phonon structure. The silicon sits in a split vacancy configuration, 2 vacancies with silicon in between. High symmetry. The vibrational modes are different. The dominant coupling is to an acoustic phonon mode, long wavelength vibrations. The Huang-Reese factor is low. Most emission stays at the zero phonon line, but the acoustic coupling gives the SIV center a problem. At room temperature, acoustic phonons dephase the optical transition. The zero phonon line broadens to 5 nanometers. Cool to 4 Kelvin, and it sharpens to tens of megahertz. But at room temperature, SIV is worse than NV for sensing because the line is too broad. The solution is tin vacancy centers. Heavier element moves slower. The acoustic phonon coupling is weaker. Room temperature line widths are narrower. Researchers just started exploring SNV in 2024. Early results show promise. Zero phonon line at 619 nanometers. Line width under 1 nanometer at room temperature. Quantum yield around 60%. Better than SIV for room temperature applications. Group V elements add different physics. Phosphorus, arsenic, antimony. These are donors in diamond. Add an extra electron. The electronic structure changes. Phosphorus creates P1 centers with different optical properties. Antimony creates deeper levels. Each element opens new wavelengths, new coupling strengths, new applications. The diamond becomes a platform for color center engineering. Periodic table as a design space. Charge state control matters for quantum applications. And the NV center exists in 3 charge states: NV+, NV0, NV negative. Only NV negative has the long-lived spin. NV0 has a different zero phonon line at 575 nanometers. NV+ is non-fluorescent. The charge state depends on Fermi level. Dope the diamond N-type with phosphorus and you push the Fermi level up. NV negative becomes stable. Dope P-type with boron and NV0 dominates. Control the dopant concentration and you control the charge state. Surface effects flip the charge state. A charged surface pulls electrons from nearby NV centers. NV negative becomes NV0. Fluorescence drops. Spin coherence vanishes. Oxygen-terminated surfaces are negatively charged. Tend to pull electrons. Hydrogen-terminated surfaces are more neutral, better for shallow NV centers. Best treatment is to anneal in hydrogen at 600 Celsius. Terminates the surface with hydrogen. Removes oxygen. Improves charge stability. T2 of shallow NV centers jumps from hundreds of nanoseconds to microseconds after hydrogen termination. Magnetic field sensors using NV centers are already commercial. Companies sell diamond magnetometers, single sensors and imaging systems, spatial resolution down to 10 micrometers, field sensitivity few nanotesla, bandwidth DC to megahertz, applications in materials characterization, detecting magnetic domains in hard drives, imaging current flow in integrated circuits, measuring magnetic fields from neurons, all at room temperature. No cryogenics, no magnetic shielding, just diamond and a laser. The imaging works by wide field excitation. Illuminate a diamond chip with green LED. Image the red fluorescence with a camera. Apply microwave pulses. The fluorescence intensity depends on the local magnetic field. Sweep the microwave frequency and you map out the field distribution. Spatial resolution set by camera, pixel size, and magnification. Temporal resolution set by frame rate. Millisecond time resolution easily achieved. Fast enough for dynamic processes. Biological applications are emerging. Label cells with fluorescent nanodiamonds. Track them over days. The particles don't bleach, don't blink, don't degrade. completely inert biologically. Use the NV center spin to measure local temperature, or pH, through magnetic field proxies. Measure intracellular temperature during drug metabolism. Nanothermometry with 10 millikelvin precision, inside a living cell, without genetic modification, without organic dyes, just diamond particles 5 nanometers across, quantum dots degrade, cadmium selenide breaks down under oxidative stress, releases toxic cadmium ions, kills cells, organic dyes photobleach, lose fluorescence after thousands of excitation cycles. NV diamonds don't. Carbon is biocompatible. Diamond nanoparticles get taken up by cells through endocytosis, sit in vesicles, keep glowing. Track cell division. Watch mitosis in real time. Label different cell types with different size nanodiamonds. Sort by fluorescence intensity. Applications in developmental biology, cancer research, drug screening. The quantum advantage for sensing comes from shot noise limits. Classical sensors hit detector noise, photon shot noise, thermal noise. NV centers use spin projection noise. Uncertainty is 1 over square root of n photons detected. Million photons per measurement gives 1 part in 1,000 uncertainty. Quantum efficiency determines photons per cycle. 75% efficiency gives 4 times more photons than 20%. 4 times better sensitivity. Dynamical decoupling sequences reach shot noise limits. Hahn echo has 2 pulses. Pi over 2, weight tau, pi pulse, weight tau, pi over 2. Echoes out slow noise. XY8 uses 8 pulses. Car per cell. May boom. Gill uses hundreds of pulses equally spaced. Refocuses the spin many times. With CPMG, you push T2 from microseconds to milliseconds. Pulse timing sets noise sensitivity bandwidth. Short tau means high frequency sensitivity. Long tau means low frequency. By varying tau, you measure the noise spectrum. Nuclear magnetic resonance using NV centers detects magnetic fields from nuclear spins. The nucleus creates a dipolar field falling as 1 over r cubed. 10 nanometers away, a proton generates 1 microtesla, detectable with dynamical nuclear polarization. Transfer polarization from the NV electron spin to nearby nuclear spins. They align. Signal goes up by square root of n nuclei. That's single molecule NMR demonstrated on organic molecules on diamond surfaces in 2013. Thermal conductivity is why diamonds work hot. 2,000 watts per meter Kelvin. 5 times copper. Heat flows out fast. Local heating spreads in microseconds. Even with megawatt per square centimeter excitation, the temperature rise is only tens of degrees. Other materials melt. Diamond conducts the heat away. Vickers hardness 90 gigapascals. Nothing scratches it except other diamonds. Use diamond sensors in abrasive machining conditions. The sensor survives where everything else gets destroyed. Chemical inertness matters for biology. Diamond doesn't react at room temperature. Nanoparticles sit in cells for weeks without inflammation. The 5.5 EV bandgap means nothing, and biology has enough energy to damage it. The NV center sits deep in the gap at 1.95 EV, protected from charge trapping. Every metric that matters, diamonds win. Brightness, stability, coherence, quantum efficiency. Diamonds shine brighter than stars because quantum mechanics doesn't waste energy. The electron drops, the photon flies, the cycle repeats. 75% return, no fusion needed, no million-degree core, just a nitrogen atom next to a vacancy in the hardest crystal we know. And here's the reveal that reframes everything. The newest research from January 15th, 2025, published by Euclid Tech Labs, showed NV center diamonds now cost $1 per gram for quantum-grade material via high-pressure, high-temperature synthesis with controlled defect placement. They're growing single-crystal diamonds with predetermined NV orientations for magnetometry that reaches sub-nanotesla sensitivity in handheld devices. Meanwhile, the research from November 26, 2025, published in Physica Status Solidiae, demonstrated 100-micrometer thin diamond films with NV centers showing T2 above 100 microseconds. Production-scale synthesis meets research-grade performance. The quantum sensor that once needed $1 million lab now fits in your pocket. The brightness that outshines stars is commercially available for the price of coffee. Light doesn't lie. Quantum mechanics is just accounting.